Thank you so much for being here. I am Albert Kim at the Department of Civil and Environmental Engineering, University of Hawaii at Manoa. I am pleased to present my recent work regarding dead-end filtration theory, entitled The Analytic Solution of Interfacial Concentration with Observed Rejection Ratio During Dead-End Membrane Filtration. This talk does not exactly follow the conventional orders of standard presentations, but has been reorganized for more efficient information delivery. The paper was published in Desalination last year. If you're interested in it, please refer to it for more details. Today, I'll present key findings. I use a reverse order of presentation, so I'll show you the final result first. There are 3 new findings in this work. Firstly, I was able to derive the analytic solution of the interfacial concentration, which is the solute concentration on the membrane surface during constant flux dead-end filtration. Secondly, the analytic solution for the decrease of concentration with time after the pressure release was also derived. Most importantly, the relationship between the observed rejection and intrinsic rejection, as shown on the right-hand side, was mathematically derived without incorporating experimental data, forceful assumptions, or correlations. Once we obtained this relationship, we verified it using experimental work published beforehand. This diagram depicts a common setup for membrane filtration. When employing dead-end filtration, the cross-flow velocity U is set to 0. As a result, the transport mechanism only involves convection towards the membrane surface and diffusing back away from it. To measure the membrane's effectiveness, rejection is often determined by calculating the ratio of the permeate concentration Cp to the feed concentration Cf. The governing equation for the dead-end filtration is given as equation 1. Initially, the solute concentration is assumed to be uniform, such as equal to the feed concentration. The far-field boundary condition of equation 3 indicates that the solute concentration is equal to the feed concentration away from the membrane surface. Equation 4 is called a mixed or Robbins boundary condition because concentration and its derivative are included in the boundary condition equation. I followed the conventional notation to write that the solute concentration on the membrane surface is denoted as C sub m. It is always convenient to use dimensionless variables. Introducing dimensionless variables often generates dimensionless numbers having physical meanings. Our dimensionless form of the governing equation is given as equation 5. We use the following dimensionless variables for concentration C, coordinate y, and time t. A representative concentration is the feed concentration, which will determine the length and time later. Lambda is a discrete constant, which can be 0 or plus minus 1. The standard dead-end filtration is represented using lambda equal to 1. 0 lambda means the pumping stopped, so the permeate flux became 0, while the back diffusion continued. The negative value of lambda is that it involves a backwashing process for membrane cleaning, which is out of the current research scope. As noted above, we did not decide the representative length scale L, which means we have the freedom to determine a Pecklet number, such as 2 in our case. With the 3 possible values of lambda, this Pecklet number gives mathematical convenience for the later derivation processes. We use the typical values of the solute diffusivity, such as of an order of 10 to the negative 9 square meter per second, and the permeate flux of 10 liters per hour. Using these 2 typical values, the representative length is calculated as 0.37 millimeters, and the time scale is about 20 minutes, which is reasonable to accept. Using the dimensionless variables defined above, we reformulated the governing equation in a dimensionless form, as well as the initial and boundary conditions. Instead of the dimensionless permeate concentration, we used the observed rejection ratio to emphasize its role in the filtration theory. All the physical meanings are kept unchanged. We used Laplace transform to solve the dead-end filtration phenomena, which is defined as follows. After many hours, we obtain a solution that satisfies the three conditions, such as equation 23. Now, we are ready to perform an inverse Laplace transform, which is the end of the solution process. This is the mathematical task of the inverse Laplace transform, which is not included in the pre-existing mathematical tables for the Laplace transform to the best of our knowledge. Specifically, the term 1 plus p in the square root makes the inverse Laplace transform challenging. Using the conventional table, equation 24 is not solvable. Instead, we can do the Laplace transform on the membrane surface. Therefore, the exponential term becomes 1, as shown in blue in equation 25. The inverse Laplace transform in equation 25 will provide the complete analytic solution of the interfacial concentration of the constant flux dead-end filtration, skipping all the details of mathematical procedures. The final analytical solution is equation 26. The first component of number 1, marked in red, indicates the initial uniform concentration, equivalent to the feed concentration. The rest of the terms are multiplied by the observed rejection ratio. Therefore, if the rejection ratio is 0, the trivial case of the no filtration case is included. The second term is linear to the dimensionless time tau. The third term is a product of a linear and error function concerning time. And the last term indicates an initial slow growth, followed by an exponential decay. Therefore, it is expected that the last term is negligible after the dimensionless time becomes more significant than 1. Let's double-check the rigor of this analytic solution by considering special cases that we already know about. First, as I indicated above, if the rejection is negligible, the permeate concentration must equal the feed concentration. This is verified in equation 27. Second, if the rejection is perfect, and therefore the rejection ratio reaches 1, we can simply drop the observed rejection ratio and reorganize equation 26 to provide equation 28. Third, when the filtration time is long enough, the error function converges to 1 and the exponential decay term disappears. In this case, the interfacial concentration is simply a linear function of the elapsed filtration time. By considering these three special limits, we indirectly verify the rigor of the analytic solution of equation 26. Equation 29 is quite simple and valid as long as the dimensionless time is greater than 1. We investigate a trend of each of the 4 terms of the analytical solution and compare them with the asymptotic solution shown at the bottom. The right-hand side figure shows all the trends of component and asymptotic solutions. As expected, if the dimensionless time tau is greater than 1, the exact and asymptotic solutions are almost identical. The first and second components show their linear behaviors, which is because the error function covers to 1 for a large tau. In this page, we plotted the interfacial concentration versus time with various observed rejection values from Z2 to 10 with an interval of Z2. Higher rejection cases have a noticeable deviation of the asymptotic solution from the exact solution, but the differences become negligible for the dimensionless time higher than Z5. This linear trend may help operators and designers of membrane separation expect the approximate magnitude of the interfacial concentration concerning time. Note that, for nanofiltration of brackish water, the representative time scale is of an order of 10 minutes, equivalent to the value of tau equal to 1. We also conducted a pure numerical analysis using the standard finite difference method. The right-hand side graph shows the difference between the asymptotic and exact solutions in magnitude. Note that the asymptotic solution is an upper bound of the exact solution. The largest difference comes from the perfect Ridgeitian case. Even if so, when the dimensionless time exceeds 1/0, the error becomes less than 5%. A good news is that the interfacial concentration increases linearly with the time after the time passes the reference value, which is approximately 20 minutes, estimated using the solute diffusivity and the typical permeate flux of 10 liters per square meters per hour. So far, our theoretical analysis is within the pressurized state with the constant flux condition. So, we rewrote the governing equation by eliminating the convection term, because the pressure release does not produce any more permeate flux after the stopping time of pumping, denoted as T sub s. Observing how long the back diffusion takes to reach a certain limiting or leftover concentration is interesting. Nevertheless, the far-field boundary condition is always valid. The analytic solution of the relaxed phase is derived as follows. Compared to the exact solution of the filtration phase, it is obvious that equation 33 does not have any terms that include the observed rejection. In equation 33, one may notice that the exponential term's exponent is positive. Even if so, the complementary error function decreases faster than the exponentially growing term. Therefore, the interfacial concentration after the pressure release rapidly decreases and reaches a quasi-plateau. This slide shows the interfacial concentration in the filtration phase, followed by the pressure-released phase with the dimensionless stopping time of 2 and 4. As expected, the concentration with a longer stopping time has a higher peak value, but their decreasing patterns are similar. Each of these two graphs shows the impact of the observed rejection ratio on the interfacial concentration profile with respect to time. The right-hand side figure is the same as the one in the previous slide. We select a specific case of the 50% rejection, shown in the yellow dotted line. The maximum concentration of this case is approximately 9 using visual estimation, and the limiting concentration at the final time of 10 is about 2. Because the total time is 10 and the stopping time is 4, the relaxing time, denoted as delta t, is 6 on your left-hand side, indicating a point with a limiting concentration of 2 and a maximum concentration of 9 gives the duration required to reach the limiting concentration. The right-hand side graph is as follows. First, to reach the limiting flux is double the feed concentration. The required dimensionless relaxation time is approximately more or less 10. However, to reach the limiting concentration of 25% higher than the feed concentration, the required back diffusion time is at least 1 or 2 orders of magnitude higher than those of the higher limiting concentrations, such as double the feed concentration. Now I want to show you one of the most important findings of the present theoretical development. Note that our work developed the interfacial concentration of the dead end filtration in the constant flux mode. A single parameter that should be predetermined is the observed rejection ratio. Previous researchers in the past decades finished other cases as follows. Dresner developed an analytic solution for interfacial concentration with the perfect intrinsic rejection case. Raridan et al. Extended Dresner's work and developed the dimensionless interfacial concentration with respect to time, having the intrinsic rejection ratio as a parameter. On the other hand, our development is for an arbitrary observed rejection ratio because the intrinsic rejection ratio is tough to measure. Now, we expect that there must be a relationship between these two analytical solutions derived independently. They used Green's function approach, and we used Laplace transform as a major solution technique. Now, we expect that there must be a relationship between these two analytical solutions derived independently. physics can be better understood by taking extreme limits. We calculated the difference between their analytical solution using the intrinsic rejection ratio and our analytic solution based on the observed rejection ratio in the asymptotic limit of a large tau. The difference is derived as equation 36, indicating that in the time asymptotic limit, the two solutions should converge if the rejection is close to perfect. So, we obtained the following relationship between the intrinsic and observed rejection ratios. Because both are smaller than 1, a square root of the observed rejection ratio is approximately equal to the intrinsic rejection ratio. Alternatively, the observed rejection ratio is a square of the intrinsic rejection ratio. Then, your question must be, is there any experimental evidence? Yes, here is an excellent one. Buranin and others did experimental research to remove glucose and cobalt solutions using a nanofiltration membrane. They measured the observed rejection ratio as 0.64 and calculated the intrinsic rejection ratio of 0.82 by fitting the data using the standard film theory. Their experimental data support our mathematical conclusion within 25% of errors. We have 3 take-home messages. First, this work developed a complete analytic solution for the interfacial concentration as a function of filtration time and observed rejection ratio. Second, a specific relationship between observed and intrinsic rejection is mathematically derived and experimentally indirectly verified. Third, the full analytical solution is coming. If you are interested in analytical solutions in membrane filtration, refer to my previous work for steady-state cross-flow filtration. This work is even more general than the dead-end filtration theories, but boundary conditions are limited to Dirichlet and Newman. Robbins or mixed boundary conditions are not included due to the mathematical complexity. The current work is supported by an NSF BPE grant, which I led the team on. If you are interested in engineering education research, especially for underrepresented or minority groups, please feel free to contact me since we are brainstorming the next phase. From this NAMS, what I learned is, I hope we can see again in the next NAMS. Thank you so much for your attention, and please feel free to leave any questions and comments on the YouTube site.